très souvent. On y va? Allez. Good morning, everyone. So I have the privilege to be the chairman for the defense of the PhD work of Pierre-Antoine Cabaret. The jury is made of two full thoughts. The first one is Thomas Pietrezak, who is full professor with the University of Lille in France. The next one is Jan van Erp, who is full professor of the University of Twente, Netherlands. Both of you are reviewers of the PhD work, so we get the floor first during the questions. The next members of the jury are the supervisors. So Marie Babel, who is professor des Universités full prof at INSA Lorraine, Maud Marshall, who is full prof at INSA Lorraine too, and Claudio Pacchierotti at University. My name is Christophe Lefebvre, so I introduce myself, and I'm a senior researcher with the University. So, Mr. Pierre-Antoine Cabaret, you have, I guess, 45 minutes, it is the rule here, yeah? 45 minutes to present your PhD work. At the end of these 45 minutes, I will give the floor to the reviewers and the examiners to ask some questions, and then we'll deliberate.
Great. Thank you. First of all, thank you to all members of the jury for being here, as well as everyone who came to attend today. So I will now start my presentation, which is entitled Design of Multi-Actuator Haptic Devices and Rendering Methods for Navigation and Virtual Interactions, for which I was supervised by Maud Marshall, Marie Babel, and Claudio Pacchierotti. So for a bit of context first, this thesis takes part in the Donnell project. This is a project funded by INRIA, whose objective is to explore the use of haptics for navigation assistance of people with disabilities. The main goal being the design of a haptic handle that could adapt to a wide range of users and mobility devices. And to do so, it aims to explore the use of multimodal haptic feedback, the use of innovative materials and fabrication techniques, as well as the customization of the device and the feedback that it provides. Notably, this project is a collaboration with clinicians trying to involve users in the design process. So the objective of this PhD is to investigate the use of haptics in handheld interfaces to provide rich sensations. To do so, our work revolved around three main challenges. The first one being how do we provide these enhanced haptic sensations within handheld interfaces? And then how do we use these sensations first within VR to enhance virtual interactions and design rich multisensory interactions? And secondly, to use them for designing accessible, intuitive, and personalized haptic navigation solutions. So, as I said, in this thesis, we are interested in haptics. That is the science that studies and investigates the sense of touch, which is a crucial sense for us humans. It enables us to interact with our environment. For instance, in such a yet simple task, it would provide both kinesthetic and tactile sensation about the shape, the weight, the friction, the temperature of the glass that is being filled here. Within haptics, we are interested in haptic technologies, haptic devices, which have been proposed over the years to provide haptic sensation for users in a variety of applications. In our case, this application being navigation. These devices can be classified in various ways. Here we chose to use the classification of Culbertson et al., which divides these devices in three main categories: touchable devices, wearable devices, and graspable devices. As part of the Donner project, our main goal being the design of a handle, we are mostly interested in graspable interfaces. So all these types of device have been proposed for navigation using a diverse set of haptic modalities. The most popular one being the use of vibration, for instance, in mobile devices, in wearables such as vests or belts, and in a variety of handheld interfaces. But other modalities can also be used. Some interfaces will use the perception of shape more globally to provide navigation information. Others will use kinesthetic feedback, such as joystick that provide forces to the users. Thermal feedback has also been investigated, or the use of skin stretch in various interfaces. In our case, we are interested in vibrotactile feedback, so vibrations. First, because it is an affordable and accessible technology, fitting in our third scientific challenge. And secondly, because of its versatility, meaning that the different properties of the vibration can be used to provide feedback in different ways, which is of interest for customization of the haptic device. So these devices provide haptic sensations, but for conveying navigation information, they need rendering methods to associate navigation information to the stimuli that it provided to the user. This navigation information can be turn instructions, so go left, go right. There can be a more global information, such as the distance or the deviation to a target, or there can also be the presence of an obstacle around the user, for instance. So these are both spatial and temporal information, and they can be displayed in different ways. One way of displaying this information is to use the location of the feedback relative to a body part or relative to the whole body of the user to provide a location information around the user. In the case where a single actuator is used, we can use temporal patterns, for instance, modulating the intensity or frequency of the vibration of the haptic signal to encode various information. And both location and temporal patterns can be used at the same time to create spatiotemporal patterns, for instance, here creating movement within the user's hand. Each of these approaches will induce a different cognitive load on the user. For instance, two complex patterns will require users to learn them and to focus on them during navigation to understand what is indicated by the haptic device. In our case, we are interested in using the location of feedback, which appear as an intuitive way of indicating a direction around the user, in which case the different vibration parameter can be used to provide additional information or more nuanced feedback. So we are interested in multi-actuator vibrotactile feedback. This approach has been largely explored in wearable devices where there is a large area on which the actuators can be placed around the user. So there are some instances of haptic belts, vests, or armbands, for example. In handheld interface, this is more challenging, mainly because of the limited space and the rigid nature of the interface that will make vibration propagation a challenge for providing distinct localized sensation within the interface. Still, there are some examples of interface that use multi-actuator vibrotactile feedback in handheld interface. There are instances of mobile phones or joystick or this spherical interface, which use some form of simple damping material, either foam or some rubber panels around the interface. Other and more recent handheld devices can use the structure of the device to mitigate vibration propagation or use actuators that have a moving part in direct contact with the user's skin. So overall, vibration isolation is not always discussed and often uses simple materials, meaning that there is an interest in choosing and designing the right materials and right ways to mitigate vibration propagation. There are also rare instances of handles and joysticks, which we are interested in the Donald project. So looking at part of these devices that have targeted mobility assistance, there has been a main focus on visually impaired users and instrumented white canes where one or several proximity sensors are linked to actuators on the device, such as here with thermal feedback or vibrotactile feedback. Walkers and wheelchairs are less common. There are some instances of walkers with vibrating handles or wheelchair with using force feedback joysticks. We can also use wearable devices that fit a more global use case. Still, most of these solutions require a new device or a heavily modified one, meaning that this could limit the access to the solution by end users. Overall, there is also a lack of customization of the haptic feedback in this approach, and there are not always evaluated with users and clinicians. So the work that we conducted in this thesis revolves around 3 axes that target part of the scientific challenge that we introduced previously. In the first axis, we are interested in the design of handheld multi-actuator interfaces that we then explore the capabilities in VR and finally in navigation. As part of this axis, we propose a total of 8 contributions where we evaluate the design of actuated tangibles and a haptic handle. We explore the use of these actuated tangibles in VR, evaluating several rendering schemes and their benefit for VR manipulation. And finally, we explore the use of a haptic handle in a variety of navigation applications as part of our third axis. In this presentation, we will focus on the selection of this contribution to highlight our methodology from our first investigation of actuated tangibles to their use to the exploration of their capabilities in VR interactions. We'll then go back to the first axis, looking at the design of a haptic handle targeted at navigation assistance, and its evaluation in two navigation applications, first with pedestrians and finally a pilot study with power wheelchair users. So first we'll dive into the first axis, where we are interested in first investigating localized feedback, understanding how we can use it, and so exploring this approach beyond the scope of the Donner project. As part of this first axis, we'll cover the design of a set of actuated tangible prototypes and their evaluation in a set of 3 perception studies. These results having been published in the TVCG journal. So we developed 2 tangible prototypes that you can see here. They are spherical, so 2 3D printed spheres of 7 centimeters in diameter, and they are fitted with a varying number of voice call actuators that are vibrotactile actuators. In the first prototype here, we have 3 of these actuators, 2 on the sides, under the thumb and little finger, and 1 at the center. And in the second one, we have 5 actuators, 1 under each finger. So with these prototypes, we seek to understand how the perception of multi-actuator feedback in these interfaces. To do so, we conduct 3 user studies. In the first one, we will look at whether localized cues are discernible from each other. Then in the second study, we look at how the amplitude balance between 2 actuators on the sides can change perceived location of the vibration. And finally, with the second prototype, looking at how accurate we are in identifying the location of vibrotactile stimulus. So here we'll cover the first experiment, where we are interested in the discrimination between localized sensations compared to the usual monolithic sensation that are used in VR, in most VR interfaces, meaning that usually one actuator is used to vibrate the whole interface. So here we consider 4 possible vibration locations within our sphere, displayed by 3 actuators. The first one is a localized vibration under the thumb. The second one is a localized sensation under the little finger. And the third one is monolithic vibration, so using the actuator at the center of the sphere. Finally, we also consider a 4th virtual location, which we call pseudo-monolithic, which aims at simulating the effect of the monolithic vibration using the 2 actuators on the sides at the same time. We explore the discrimination of these 4 possible locations in combination with 3 waveforms. So they are representative of signals that we could use with this interface, either in VR or other applications. So we conduct a user study with this, considering these experimental conditions. This first user study was conducted with 16 participants, and the task that you can see here was to identify the odd stimulus in a sequence of 3 vibrations within the sphere. So for instance, there are 2 vibrations on one side, 1 vibration on the other, and the participant had to identify which one of the 3 was different. Looking at the summary of the results, you can see here the median identification rate for each location pair in combination with the different waveforms. What we can observe is that first participants are able to discriminate between the monolithic vibration and the 2 localized vibrations from each other. Secondly, the pseudo-monolithic feedback is more confused than the other vibration, but it is still somewhat distinguishable from the usual monolithic feedback. And confusion is especially high with impact vibration that have a shorter duration. Will not go into details over the two other studies, but here are the main takeaways. In the second study, so we studied the use of the change of the amplitude balance between the two actuators, and we showed that it could yield the information, it could yield the sensation of intermediate location within the sphere, which could go up to 7 virtual locations for long vibrations such as the noise and the sine wave. But this effect was not treated for shorter stimuli, which did not benefit from this effect. Finally, in the third study, we looked at the ability of participants to identify the location of vibration with 5 actuators within the sphere. Their accuracy was around 1.2 centimeters, which means that they were able to locate vibration within between finger distance. And this time there was no effect of the waveform on the performance of users. So overall, we showed that these tangibles, these actuated tangibles that we design could yield passively localized sensation within the user's hand, and that funneling could be used in some cases to increase the number of virtual locations in the sphere. So now the question is how we can use these localized sensations, and we explore these possibilities within our second axis, focusing on multi-actuator feedback for VR interactions. So here we'll first look at this second contribution, in which we are interested in the design of rendering schemes that exploit these capabilities of the interface and their potential benefits compared to the usual monolithic feedback used in VR. Here we'll cover the design of these rendering schemes and the evaluation of their benefits in VR, which were part of the same paper published in TVCG. So here are 6 of the virtual interaction that we designed using this tangible prototype. Here you can see, so they all provide haptic sensations when they are performed. We have a vibrating object with a mass that is moving on one side or the other of the object. We have a pulsating object that shrinks within the user's hand. We have a sphere with liquid inside, the exploration of texture with a rigid probe, and the perception of the sensation of impact either within a handheld object or on a larger handheld object. So here we are interested in the coherence between the visual and the haptic feedback. If we focus on this example here, we have a virtual source of vibration that is visibly on one side or the other of the object. So here we design for each of the rendering scheme that we presented 2 versions of each one. One localized version that uses the actuator that is more closely related to the vibration source to display the sensation, or using only the actuator at the center, meaning that this would be a monolithic version of the rendering scheme. We evaluated all of these rendering schemes in a user study with 21 participants, in which they had to perform each interaction several times. And for each of these interactions, they had to choose which one felt the more coherent between the visual feedback and the haptic feedback that was displayed. Here is so a summary of the results of this study. Results show a significant preference towards localized feedback in 2 of these interactions, namely the vibrating object and the liquid filled object. And for other interactions, there are no significant preference, meaning that this type of feedback can be beneficial in some cases, while not being detrimental in others. In a third contribution, we followed up on this study, exploring further the use of the spatialized sensation, this time to display the direction and distance of impacts in VR. We'll not go into details over this contribution, but results were published at EuroHaptics 2022. So to finish up on this second axis, we proposed a set of rendering schemes for VR, some which benefit VR interactions, and we showcase their integration in VR as seen in this aggressive virtual environment. There are still some limitations to this approach, including the fact that vibration propagation was not considered, which limits other uses, including the ones for navigation, which requires more distinct sensations. That is why we'll now go back to our first axis, where we will address this challenge of vibration isolation. So here in our first axis, we'll now go over the design of a multi-actuator haptic handle with the objective of providing localized haptic feedback within the user hand, designing a structure that would isolate vibration, and following this with the validation of the proposed design through a set of studies, part of which were published at EuroHaptics 2024. So the haptic handle can be seen here. Its specificity is the presence of 4 actuators on the sides, which aim at providing 4 stimulation points within the user hand. The handle is 3D printed, making it relatively easy to build and to customize. As I said, so we have 4 stimulation points within the handle, and we can see here this yellow structure. It is made of a deformable material, and so when the user presses on the handle, we can see that the different modules bend. This structure has 2 key roles in the design of this handle. First, it aims to isolate the vibration within the haptic handle, and secondly, it also ensures the contact between the motors and the user skin. So this design is a result of several iterations, and so now we'll cover its validation through a set of studies, first validating the effectiveness of the structure, and then exploring the ability of the haptic handle to provide directional cues to the user. So first, we evaluated the effectiveness of this deformable structure compared to a rigid version of the handle, meaning that the structure inside was printed out of rigid PLA. And so in this study, we used an optical vibrometer to measure skin displacement velocity at 4 points around the user hand at the level of each motor, while only activating the motor here at point A at 10 level of increasing vibration intensity. You can see part of the results here. What we can observe is that here vibration are up to 10 times stronger at the stimulated point A with the soft structure compared to the rigid one. And secondly, the difference in vibration intensity between the stimulated point and the adjacent point is much higher with this soft structure, thus validating the effectiveness of this design. Following up on this study, we conducted a user study in which we evaluated participants' ability to discriminate between the 4 vibration locations, again using the 2 versions of the handle. Overall, participants were able in both cases to discriminate between the 4 locations with some better results for the soft structure with 91% accuracy. But the main result here is that when asked to evaluate the difficulty of the task with the two handles, difficulty was evaluated much higher with the rigid one, again confirming the interest for this isolating structure. Secondly, we compared two approaches for displaying 8 directions using this handle, either using sequences of vibrations or the simultaneous activation of two motors. So here, for instance, to display the front right direction, we'll either use a sequence starting with the front actuator and then the left, or using the front and right actuators at the same time. In these cases, accuracy is lower than in the previous study, with 65% discrimination accuracy for the dynamic patterns and 75% accuracy for the static ones. But interestingly, performance is tied to participant, meaning that learning and training with these different haptic patterns might help improve performance. So to conclude on this first axis and the design of this handle, we did a simple evaluation of the use of the device here to navigate in a virtual maze, which confirmed the effectiveness of the handle to navigate in a simple task. So overall, we proposed the design of a haptic handle, providing localized sensation within the user's hand, which can display up to 8 directions to users. Now we'll explore the use of this sensation to provide more navigation information as part of our third axis. So the third axis is made up of 4 contributions, which will not all go into details with. In the first one, we continued our use of VR to explore what we could do with this haptic handle in a navigation context. Here we used the haptic handle as a representation of the users and their surroundings, evaluating the ability of the handle to inform of the direction of moving obstacles and to represent to indicate presence of virtual characters or objects in the user personal space. Following on this study, we continued with pedestrian-based navigation. This time we will cover the design of navigation strategies to guide users along path and their evaluation in a user study, which were published at Eurohaptics 2024. So we design our navigation strategies to guide users along target path. Each strategy working in the same way, meaning that every strategy will, based on the user position around the path, define a target for him to follow. Then it will compute the angle between the user-facing direction and this target direction. And finally, it will map the angle to a directional information that will be displayed by the handle. The handle can display this information using 2 rendering schemes that are based on the previous directional stimulus that we evaluated. The first one uses 4 directions, so each motor is linked to one of the directions. And the second one uses the simultaneous activation of 2 motors to add the diagonal information to this rendering scheme. So we now go over the 3 strategies we proposed. The first way of providing guidance feedback to user would be to regularly provide them a direction to follow, which is what the attractive strategy does. So it works by taking the closest point from the user on the path and then setting the target to a point 1 meter ahead of it. and then it maps this angle to one of the directional stimulus, which will be displayed regularly every second. In this case here, the user would be guided either towards the left using the first rendering scheme and towards the front left using the second one. Another way of providing navigation feedback would be to indicate when users are deviating from the path. This is what the repulsive strategy does. Here we consider a zone around the path where users do not get feedback when they are within this corridor, but when deviating from the path, for instance here, they will get directional feedback regarding the direction in which they are deviating. So here, for instance, when moving away from the path, they would get the front direction information, or the front right, meaning that they are deviating in front of them. And a third way of guiding users, instead of indicating deviation from the path, would be to indicate the way to get back onto it. This is what the latent attractive strategy does. It works in a similar way as the repulsive strategy, but this time the feedback that will be displayed to users will be the direction to get back onto the path. So here it would be the back direction or the back left direction using the second rendering scheme. So to evaluate the use of the handle as a navigation device and the combination with these different navigation strategies, we conducted a user study with 18 participants, which took place in a controlled environment, which is a room of 8 by 8 meters. Here you can see a participant which is following the instructions of the handle while walking. And so each one of the participants tested all 3 strategies combined with the 2 rendering scheme, so for a total of 6 combinations, each time on 3 reference paths that you can see here, which were designed to take into account different angles of 90 and 45 degrees and different segments length, either long ones or shorter ones. Looking at the results here, you can see a sample of good trajectories for 2 participants on the same path. So each column here, the first one and the second one, are 2 different participants across the different navigation strategies and the different rendering schemes. What we can observe is that overall the attractive strategy produces more smooth trajectories than the other, which is coherent with the fact that here participants had to move away from the path before getting any feedback, which can be which produces these bouncing patterns around the path. Between 4 and 8 directions, we can also observe that trajectories appear to be smoother here due to the higher granularity of the information displayed to users. When looking at successful trials, meaning trials where participants reach the end of the path in less than 4 minutes, we can again see an advantage for the attractive strategy, but still the 2 other repulsive and latent attractive strategy perform up to 80% accuracy. So during the experiment, participants also answered a questionnaire. Looking at their answer, we can see that they found the first attractive strategy to be easier to use and to learn. However, some participants did report that compared to the other strategies, it did not inform them of whether they were succeeding or not, making it difficult to know how they performed. Between the 2 rendering schemes, participants evaluated here the use of the ease to locate the vibration higher for the first rendering scheme. But overall, when asked which one of the 2 rendering schemes they preferred, there was no a clear preference between the two. So following with our seventh contribution, here we get back to our objective as part of the Darnell project, where we want to investigate the use of the haptic handle combined with here the first navigation strategy with a power wheelchair. Doing so, we also evaluate whether the location of feedback could have an impact on navigation. So evaluating whether placing the haptic handle in the non-driving hand or placing the handle on the joystick that is used to drive the wheelchair would have an effect on navigation, whether on performance or the comfort of users. So we conduct this navigation study with 16 participants using a similar experimental setup, this time adapted to the power wheelchair. Here you can see one of the participants driving the wheelchair while following the navigation instructions. Looking at the different trajectories of participants, here you can see all trajectories superimposed over each other. At the top for the first rendering scheme with 4 directions and here with 8 directions. Overall, we can see that participants are able to follow the global shape of the path with some more variations with 8 directions in the turns and more difficulties in the second pass. Overall, we did not find any clear impact of feedback location between the two positions, meaning that it could be used both ways. And however, this confirms that participants are successful with using the haptic handle to navigate, in this case, with a power wheelchair. So for our final contribution, our goal was to continue this evaluation of the use and acceptability of the haptic handle, this time with real users of power wheelchairs, which is an important step towards the use of haptic navigation solution by end users. This study was conducted in collaboration with Paul Saint-Hélier, Rehabilitation Center here in Rennes. And this study was made of 2 parts, which aimed to evaluate the discrimination of haptic patterns displayed by the handle and their use in navigation. Here, the participants' profile were more diverse than in the previous experiment. We had 10 women and 4 men from 27 to 74 years old, which had various pathologies that led to the use of a power wheelchair, the majority of them including strokes or MS. All of these users were users of power wheelchair, with 3 still being in the learning process. And these profiles were also evaluated using the wheelchair skill test questionnaire and the 2-point discrimination test to evaluate their tactile sensitivity profile. So the navigation study used a similar experimental setup as the previous experiment. It took place in a large space of 12 by 8 meters, in which we used 3 target paths combined with the 2 different rendering schemes. And here you can see one of the participants driving the wheelchair, well, a virtual representation of one of the participants driving the wheelchair, following the navigation instructions. On the left, you can see some of the trajectories here for 3 participants between 4 directions and 8 directions. Overall, trajectories are more diverse than in the previous experiment, but we still see less deviation and failures with the first rendering schemes, and we observe that 90 degrees turn here in the second path are much more challenging. And here you can see some more diverse instances of participants that were not able to follow the navigation instructions correctly. This can be in part explained by the task itself. Given that there was no ecological goal, the task was rather difficult, which adds to the fact that participants did not know what the shape of the path could look like, which also adds to the failure sensation of some participants. During this experiment, participants also evaluated their global workload, which confirms that, again, aid direction here, the use of aid direction was much more demanding and difficult, and highlighting that the navigation task, again, is more demanding than the pure discrimination task. We also evaluated the acceptability of the device by users using a UTOD-based questionnaire. Overall, the use of the device itself was evaluated positively, but the transmission of the information was found complex and required effort. And overall, participants did not project themselves into the use of the device, which is quite coherent with their profiles, as there were drivers that did not need additional guidance. However, they thought that other users and therapists could see an interest and benefits from the use of this device. So to finish up on this first axis, on this third axis, this contribution showcased the versatility of a haptic handle, first investigating its use in VR before exploring the different ways it could be used, validating it through several user studies, leading up to a final pilot study with real users. So I now conclude on this presentation. So to summarize, in this thesis, we proposed the design of activated tangibles, which provide localized sensation within tangible objects, which can be beneficial in some VR applications. We followed on the design of a haptic handle addressing vibration isolation with a 3D printed isolation structure, and evaluating the ability of this handle to display a set of directional cues. Finally, we explored the use of the haptic handle in a variety of contexts, showcasing the different ways it could be used, and concluding with a first evaluation with power wheelchair users, which provide valuable insights for future work in this direction. Finally, as for the perspective, there are multiple directions in which future work could explore. Regarding our initial approach of mixed haptics for VR, we could apply our work on vibration propagation to these devices, as well as explore the use of additional haptic modalities. And the combination with encounter type haptic display could also mitigate the current limitation of having the tangible in hand at all times. Regarding our haptic handle, the current design is fixed and could be adapted to users depending on, for instance, their morphology or their grasping position. And it could also be adapted to other mobility devices. The use of more precise actuators could also allow for the display of a larger range of haptic sensations. And the integration of sensors could allow users to interact with the device. Finally, as for the navigation application of this handle, the current tasks, as I said, were performed in a controlled environment, which is far from the use of the device in a real environment. And thus, the next step would be to evaluate this device in other contexts. Additionally, we could explore further the customization of the haptic feedback, letting user in control of how this information are displayed to the user. And so that will be the end of my presentation, and I'm now ready to take your questions.
Thank you. Thank you for staying in time and doing a nice presentation. So now it's time for the questions. So we're gonna go, as I mentioned previously, first with the two reviewers. So we'll start with Thomas Pietrzac for 20-25 minutes question. I can tell you when you
Yeah, you can stop me if I get wrong. Usually I'm like, it's going to take 20 minutes and then half an hour later. So don't take
Then I'll give the floor to Jan van Heff for the same duration, approximately. Then I'll remove my hat of chairman and then ask you some questions as an examiner. And then I'll give the floor to your supervisor, and I'll take back the floor for ending the session. So, please, Thomas, you can start.
Well, thank you very much. So, I have to start the same way I started my report by congratulating you, because it's really, really a lot of work. Like I think there is enough for 2 PhDs. Some PhDs don't do half of this. So there is a lot of quantity and there is a lot of quality. So I was very, very pleased to review this work, and I followed this work during the PhD, and I was very happy to be part of the committee and to give an assessment of this. So congratulations.
Thank you.
So continue like this. So my job now is to make it a little more difficult. So yeah, so I ask questions more in the direction from start to bottom. So my first question is maybe an easy one, but with the first prototype we could see here.
Yeah.
Why did you choose a sphere?
Okay. Here. So for this first prototype, we chose a sphere, well, for different reasons. First, we had in mind the use of this sphere for VR interactions. And so the use of a spherical object would be like the simplest shape that could represent various virtual objects in VR. So it would be like the more generic one that could fit, for instance, the well, it was in the virtual demo, holding a bottle, holding another object. So that was the idea of having the generic shape. And we had also in mind that it could be combined with the encoder type haptic display that we have, which is also a spherical one, and which fits nicely around the hand, while having the different actuators placed closely to each of the figure.
So when I was thinking about this, one of the good things with the sphere as well is that there is no edge, which means that you cannot feel something you're not supposed to feel. Maybe.
Yeah, which is why it's good for
Holding like this object in virtual reality, and imagine that it's a cube, and you will feel an edge, and you don't see the edge here.
Yeah, that is what I meant with the more generic object. Meaning, you don't have any parasite sensation of edges or the most more global shapes of the object that would change your perception of the virtual object that you are interacting with.
Okay. And how did you choose the location of the actuators and the number of actuators? Can you build the layout?
Yeah. Well, we designed 2 actuators. This one was really this one was more related to the interest of using the funneling illusions between the 2 actuators on the side. So it was, well, it's a bit like the most, the end goal of having the most actuation point within the sphere was with the second one here, where it was hard to add more than 5 actuators within this one. And we felt like having 1 actuator per finger was the most that would be interesting for VR interactions. And with the first one, it was, well, the most simple approach for multi-actuator feedback, meaning that multi-actuator feedback starts with having two vibration location. And so for first investigation, it was to look at whether the approach would work with two actuators, and then we could go up in numbers or use the funneling illusion to provide virtual location within the sphere.
And have you tried funneling illusion with the one on the bottom? Like to have something that feels like moving across your fingers?
We did not try the funneling between two actuators within this one, but yeah, we could display moving motion across the different fingers.
And then, how and why did you transition from this to the other handle?
To the
other prototype in the other study?
Yeah. So this was for the first investigation of actuated tangible and multi-actuator feedback, and so this was fitted for VR interactions, and the haptic handle itself was designed. Well, first it was easier for vibration isolation to be in the hand, to be in the shape of the handle, rather than in this spherical version, where it is harder to position correctly the different actuators. And also the idea behind the handle was then to use it with different mobility devices or in different navigation interactions. So we kept this idea of having a handle that could just fit within the hand, that we could put on a wheelchair, and that with some changes of the design, we could maybe adapt to walkers or white canes, for instance.
So later, I want you to comment on your mapping for the directional instruction.
Yeah.
Because you mainly encode directions, but you mentioned that you can also encode distance. So have you encoded distance, and how would you encode distance, for example?
Yeah, so we mainly encoded directions. Distance, we encoded a bit of distance on the on here this study. In these cases, distance was encoded, so the direction of, for instance, here the presence of an obstacle was usually, on this one, on the personal space, the direction in which there is an intrusion of the personal space was indicated with the first the location of the vibration around the handle, and then the proximity of this presence was encoded using either the vibration intensity or the vibration frequency. This is something that we did not explore further within the other applications, but with the vibrotactile cues, we could use the intensity, frequency of vibration. Maybe with other actuators, we could use different signals to encode this proximity information.
And what about like more complex instructions, like asking to do U-turn or something like this? Do you consider this kind of stuff?
So one way of doing that would be to more rely on the apparent motion illusion, for instance. So we could try to activate different actuators with like some sort of rotating motion. At some point, we tried that to first just continue on the indication of direction. So, for example, to turn on the right or on the left, we would use the activation of 3 actuators. So, for example, right, front, and left. to create some sort of motion towards the left side. But with this handle and the localization of the feedback, users mostly relied on the information of the last vibration to know which indication was provided. So it was not really the trade-off being the duration of the signal being longer compared to the fact that it provided the same information was not really interesting in this case. But it could be used to provide more information than just turn instructions. So for instance, turning around, also the success to a task, or if we imagine an application with moving within a real building, we could probably provide some information about elevators or stuff like that using different patterns on the haptic handle. I don't know if that answers your question.
Yeah, because I was thinking about when you use a GPS, for example.
Yeah.
It doesn't say only turn right or turn left. Basically, there is a kind of taxonomy of instructions. So you have to turn right or left. You have a U-turn. You have the roundabout, take the first, second, or third exit, something like this. Or if you have a fork, at the fork, take the left or take the right. And there are a couple of instructions like this. So I don't know if you check these kind of things, or maybe it's not relevant to what you would like to do.
A roundabout might not be really the most suited use case for this haptic handle, but there are some papers that encode this information, for instance, with like if you are at an intersection, there are several vibrations, one for each of the road that you could take, and then one of them is more distinct than the other to tell you to take this one. Something that we prototyped at some point also was to indicate more nuanced turns than just left or right, would be to have a sequence of 1, 2, or 3 short vibrations on one side or the other that will tell whether you have to turn a bit or really turn a lot, towards one side or the other.
Okay. So yesterday I tried the wheelchair with the sensors, and we were talking about haptic feedback basically. So one thing is that this kind of device can sense obstacles and stuff like this, and they can say, okay, you should not go this direction, and guide you to some different place because they feel like this is not a place where you would like to go. But maybe the user wants to know what's there exactly and wants to know more, maybe why they should not go there. Do you think so? Usually, because we think about the haptic feedback and give information, but maybe the user wants to get information, and the system can go both ways sometimes. So have you thought about, or maybe it's not relevant, of a way for the user to ask for more information to understand why this guidance is guiding them in this direction?
Well, we thought about combining the handle. Well, this is something that we want to do, of combining this haptic handle with the wheelchair that you tried yesterday. In this case, it could indicate the presence of obstacles maybe around the user. What could be interesting, yes, is the fact that the user would be in control of whether he wants this information or not, which for now is limited because the handle doesn't have like a way for the user to communicate with the device. But we thought about putting, for instance, a button on the top of the handle. And so maybe in a case like that, that could be a way of asking the wheelchair or the handle to tell why it can't move in a way or another. But that would that could display also the proximity of obstacles or dangers around the wheelchair, I think.
And sometimes, so there is like the inverse as well. Sometimes you follow the GPS, it tells you to go like just in front, and you know that the road is blocked, so you want to have a different instruction. Sometimes you're driving, there are people behind you and so on, so you don't want to mess with your device. So you take a random route and hope that he will not ask you to do a U-turn and to do this sort of stuff. So sometimes there must be ways to say, okay, forget about this solution. I know that I cannot use this solution, find me another one.
Yeah. This is a combination between the navigation strategy at some point, I think, because if you deliberately change the route that you are following, maybe this is to the system to compute a new one following what you did. But here what is missing is probably some way of the user to say to the system that it needs another route or another guidance by the haptic handler.
So this leads a little to my next question, because usually when we are on a haptics, we're talking about perception. And perception is into action. I'm talking with an expert in cognitive science here. Especially so with the effects, the haptic effects that you design, and you check that people can feel and understand the effects. Yesterday I tried for the liquid. So with the liquid, to really feel a liquid, you have to move your hand. So in this experiment, did you move? So did the person move the hand?
For the VR experiment?
Yeah.
Actually.
Because what you perceive is, especially in this case, very linked to the brain.
Yeah. So in maybe the video will start. So here are the videos within the experiment. So each time the participant was instructed to perform the interaction with a virtual counterpart that told him which movement to do and at which speed to do it, so that it's relatively consistent across participants. So for these moving parts, there is this hand that is moving and the participant is also moving. And for the texture exploration, this one was always active, but they also had an indication of the speed at which they had to go across the two surfaces. And for the two others, however, the participants were mostly static, so they could see the object move their hand a bit around, but there was no effect of their motion in this case.
And if I remember correctly, people had difficulties with the impact to locate if the impact was on the left or on the right. But if I had a bar like this and it's something on the right or on the left, would I be able to if the heat was on the right or on the left?
Yes, there were studies that looked at that and that showed that we were able to know on which side was the information, whether using only vibrotactile feedback or when there is force feedback, it's more evident to the user on which side are the impact occurring. In this case, it was not that, in this specific case, it was not that participants were not able to know on which side was the vibration occurring. It was more that they did not have a preference between the monolithic and localized versions of that, because in this study, the participants were able in I think it was 90 or 95% of the case to identify on which side was the vibration occurring, but they had difficulty evaluating the distance, which is much trickier in this case.
So you designed several effects, and this is already impressive because it's supposed to design one effect, or design several of them. So these are effects similar to something that exists. So have you tried effects that doesn't exist or which are not possible physically? Because this is what is interesting in virtual reality, that you can create something
In this specific case, we did not design really unreal effects. For the, well, here I think it's maybe more interesting to design realistic effects because we have expectations of what the haptic sensation that we would have look like, what feel like. And so it might be easier to know whether this is coherent or not. Because if it's a purely new interaction, maybe you don't have expectation of what the feedback would feel like. But no, we did not explore the use of really other interactions than these ones.
Yes. At least 5 minutes.
Okay. Yeah, so like 30. So we see like
This one?
yeah, right, yeah. So you have 4 points,
Yeah.
and basically you show that people feel differently depending on the point. So did you plan to change like the flexible parts depending on the location to make it like homogeneous or something like this? Is it possible, you think? Make, for example, C steeper so that it feels a bit more like A or something like this?
Huh. Well, we did not investigate how different the different vibrations feel to the users, more like the discrimination. But yes, there was for instance more confusion usually with this back direction or location. Here, the stiffness I think is well, it could be explored, but I think here what should be done is more looking at placing the, so here the structure is entirely symmetrical. Probably one thing to do would be to have this one a bit longer so that it is more in contact with the palm, which for some users could have, the contact between the actuator and the skin here was less pronounced for some of them. So this would be what I would change here is maybe customize this part to have the motor come out of the handle a bit further. And in this case also maybe the motor, instead of being completely vertical, could be so sideways, so the structure could be changed a bit in this direction.
Yeah, because from what I tried yesterday, when I had it in the hand, the thing is that the C1 is just at the junction here. The other ones are touching bones and basically I think there's a lot of mechanism receptors, but this one is a very specific place of the hand, so maybe the sensation is just way different.
Yeah, so maybe, either it could be placed a bit lower in contact with the palm instead of being purely at the junction here. And otherwise it could also maybe be placed a bit differently. Maybe we could move it a bit to one side or the other to have a bit more contact with the end.
Or maybe try with more than 4.
Or maybe Well, we could try with more actuators, but I think even this one would not be always necessary, I think. So for instance, in the power wheelchair navigation tasks, this is a direction that was usually not used, or less so, because you don't have to like move around and get around all the time, and that could be just replaced by a turn to the right that is more long than the other. So that could also mitigate the issues of perception with this one, maybe not using it and relying on the other actuators that are better perceived to give the same information.
I think I can stop here. Okay, so thank you very much.
Thank you.
Thank you, Thomas, for the first set of questions. And now give the floor to Pierre for the second set of questions.
Thank you, Mr. Chairman. I would like to underline the words of Thomas. It's an impressive amount of work with excellent engineering and many user stuff. So I really enjoyed reading your thesis. I have a lot of earmarks. I don't think we can discuss them all. I would also like to congratulate your supervisors. In science, you all stand on the shoulders of the ones who were there before us. And considering your work, I guess we can consider you as a new expert. And being an expert means that you know what does work, but also what does not work. And anybody can read the papers where we proudly present what works, but knowing what does not work is at least as important. So imagine I would be a new PhD student following in your footsteps. What would your top 3 advices be not to try? Because you don't know.
That is an interesting and hard question. Well, what does not work?
Everything works.
That would be great, but no. I would say, well, first, there are, well, it's more related to the VR studies with the obstacles and virtual characters, stuff like that, where we try to see effects of haptic feedback, but the visual feedback was much more, well, it was predominant in these cases, so it was, yeah, it did not see any, it was hard to see any effects in such tasks. And so, yeah, I would advise not to use haptics in these cases where the visual feedback is really dominant over everything else. And yeah, I'm not not sure what else I would have to say right now on these devices.
This is an opportunity to share your frustration. But,
no, the other thing is maybe, yeah, in the navigation tasks, maybe rely on more simple tasks first to evaluate this navigation performance, because we chose really, well, we chose interesting trajectories, but this is especially hard to now understand what is actually going on along these, especially the trajectories that we had with real users. They are really erratic for some of them. And so right now we are still trying to see what we can learn from them and how we can treat them correctly.
so even your failures are interesting. I'll get back to that later, I guess. Because I actually want to start with your first set of experiments. And, so I tried your sphere yesterday,
Yeah.
and it turned out that I'm, again, not really a typical participant in your study, because basically I experienced the impact waveform to be better localized than the sign.
Yeah.
But you find the opposite effect in your average population. So, I was just wondering, why did you choose different waveforms? What were your expectations to start with?
So the different waveforms were chosen. So for the first, like, more perception experiments. Yeah. Well, this was when we did these prototypes, we had this VR application in mind. And so the three waveforms are representative of the different signals that we then use in the different rendering schemes. So for instance, well, the sine wave was just for the vibrating object or the haptic bits perception, but for the noise was more related to the texture rendering that we use, and the third one was the impact. So it was more related to the two rendering scheme that uses impact also.
Okay, in your hypothesis, you basically state that you don't expect a difference in performance for localization related to the three waveforms, correct?
Yeah. Well, yeah. We did not expect any differences. Well, mostly because trying the different effects, I felt like they were all perceivably localized, but that is variable among participants. So yeah, the hypothesis that it was that if the vibration were sufficiently localized, it would be the case with all of these waveforms, which was in fact which was mostly the case for the discrimination of this vibration, but this is more for the more complex effects that there were differences among the different stimuli.
Okay, I was wondering to consider not in the use case of rendering different.
The latent interactive strategy added the cognitive process of having to reverse this information and knowing that we have to get back onto the path. So maybe it's just that the repulsive one is more known already by participants, which could explain why they perform better with that.
Thank you.
Are you done?
Well, actually, but the time is up.
okay.
No, it's fine. I'm going to say fine.
2 seconds.
So I'm gonna take the floor for an additional set of questions before giving the floor to your supervisors. First, I join Jan and Thomas congratulating you about the amount of work you've achieved during this PhD. You've gone from the prototyping to interaction design and evaluation. And I think there are strengths in your work, as they mentioned already. So the prototyping was really impressive. Experimental design, statistics analysis are good, according to me, except, I mean, we can have some discussion on
yeah, probably.
some topics, but overall, I think it's very good. Evaluation, experimental settings, so the simulation, the chair, everything. And you managed to publish that in good venues. So, I mean, it's a very good set of PhD work. And today my point is not just mentioning that you achieve a very good work. So I'm going to go on some of the weakness of your work. And my point here is more, I'll succeed in chatting with you today if you consider a bit more what I'm going to say in the next years of your career. So I also join Jan and Thomas about congratulating the supervisors because I mean, the settings, everything, probably they have been providing very good support to you. So I have 3 or 4 pages of questions. So I will skip the very specific one that we can talk about face-to-face later on if you want, and focus on more general questions that have been addressed for some parts already by Jan and Thomas. But I would like to come back on that to make maybe more conscious. And I have 2 sets of questions that are on system and interaction design, and another set of question that is on market and innovation. So, if I start with system design, so you've been asked, why did you choose focusing on handheld device? Why did you choose a sphere and then a handle? So, would you like to recap for me why you choose these form factors?
Yeah. Well, so these two form factors were really chosen depending on based on the end application where we wanted to use them. The spherical shape being also a more exploratory device that we could play with. But I think I already forgot the the last part of the question. Yeah, sorry.
If I can comment on that, and maybe you can react. I think there is not a unique device for haptic feedback.
Yeah, of course.
And this
Yeah.
is the main point. And it depends on the context and the task you want to achieve with it. So this is my point. Probably you don't consider enough the task and context you want to provide haptic feedback to.
Okay, so that the device are maybe not specific enough for the
No,
for this
probably
task?
the way you describe it in thesis is not specific enough.
Okay.
Because if I go to, let's say, you were talking about blind and low vision people using haptic device. Do you think one of these is adapted for them walking in the street?
Well, first, not really, because either the device is handheld or placed on a power wheelchair, so we did not investigate the use. I think the most appropriate one would be to adapt on a weight cane or an existing device that users are already used to. And yeah, maybe in the case of visually impaired users, this is also not the most adapted haptic modality, being that if they use a white cane, there is also already mostly vibration information perceived by the white cane, the impacts, the rolling on the floor. So adding onto that other vibrotactile modalities, other vibrotactile sensations might not be the best suited information for that.
I think this is a point of view. This is yours. But you know, there is one system that exists already, one device that has been sold.
Yeah, there are already existing devices for that. Yeah.
Adding haptic feedback on the long cane, the white cane, providing feedback about as having a longer cane, so can reach 2, 3, 4, 5 meters away, and some users are experts. So you are right that you have to consider providing feedback on existing one, because the cane is probably real-time feedback. But then it's possible to use haptic devices to give more feedback to the user. So I think the point here, as you mentioned, is more what is the context and what is the task and what are the users. And this is probably one of the aspects you didn't consider enough, to me, because I'm more focused on this kind of questions that you didn't consider enough in your work.
Yeah, well, especially the evaluation with real users arrived really towards the end of the thesis. So I think that if we had a bit more time, we could have maybe had more feedback of users and maybe adapting the device accordingly to conduct other studies, maybe in more related to their needs than the experiment that we did here was really translating what the other studies that we did with real participants.
I fully agree that evaluation with users is a very good point. And you did it, I mean, many times, and impressively, I would say, because you have these chairs, wheelchairs in the big room, and etc. But what you didn't do is needs analysis before prototyping, which can help to better design the devices.
Yeah.
One point would be, for instance, you didn't consider morphology and physiology. So Jan and Thomas, I don't remember which one, were asking, okay, is it the best form factor? Could you move a bit the vibrator to this part of the hand? One way of answering that more systematically is knowing where are the nerves, what are the more sensitive part of the hand, where to place, to locate the vibrators and all this stuff. And this you didn't mention, so maybe this is something you know, but you didn't mention in the manuscript, I guess. Did you?
So first, I address the evaluation of the needs. That is not something that I did, but which was done by other partners within the Donner project. So at the start, asking users of various mobility devices and also therapists of what they would envision the Donner project, the Donner handle to be, and that is part of what guided us towards this this design also, and the use of vibrotactile feedback, because this is what they were envisioning the most as the haptic modality that would be used by the handle. And yes, I agree that maybe the placement of the actuators in these specific devices could be more precise, or consider more the how we perceive touch. In the first studies, we were given the size of the actuators that we used. We were more stimulating a large area, so I think that it might have an effect of considering where the vibrations are located, but we would still be able to display the 5 different locations. But
just to conclude on this aspect, because I wanted to talk about interaction design, not only system design, device design. I'm not convinced that you really consider the hand morphology, but probably it makes sense starting as you did. I want to go to interaction, and maybe before going to interaction design, I'll come back to the user needs, because the two devices that you designed during your PhD work, none of them is adapted to blind and low vision people, and we'll talk about that later. And I want to ask a question about that later too, about what are the needs of the people on the wheelchair, and why. But I'll come back on that to that question. I first switch on interaction design. So do you think so you mentioned in slide 6, I guess, the 3 type of information you can provide to the user with haptic feedback. Do you think this is exactly what the users need? I mean, following a path very accurately. Do you think this is the main thing they want to get? And let's just considering people in a wheelchair or blind or low vision users.
Yeah. Well, probably for blind users, I think the needs would be quite different. That's what we proposed here, given really the navigation task. Blind users would probably prefer to have information about what is around them, or the dangers that the potential dangers that are around, or maybe more global navigation information. So if you had to go somewhere, information about the planning that might be harder without vision. For wheelchair users, here the task was really specific and really targeted at following a specific shape. I think in a more real use case would be closer to the use of a GPS, for instance. So the turns wouldn't be that there wouldn't be that much turns and at such shorter distances, but would be maybe the help to navigate within a building to guide them towards a goal that they don't know where it is.
There is something I don't understand because for me, I've been following a very accurate path.
Yeah.
You don't need the user. You
Yeah.
can do with the device. I mean, the wheelchair can do on its own and can follow a path much more accurately than the user. Do you agree on that? So what would be
I agree that having a motorized solution would be the most accurate solution to guide users, but letting the users in control of the device and what it does and where it goes is really important for them in designing such solutions.
I fully agree with you on that. That's why you should go to user-centered design. Because what you provided, and I've read the feedback from the users in your manuscript saying, I don't consider using it. I don't like it. And it makes sense to me because, I mean, following the path, this is not their needs, actually. Their needs is more like, I want to go there. Or I want to stop. Or I want to chat with my friend, which is here. So, and this is a higher level control of the chair, not just following the path.
Yeah.
So I think this is one of the the design step that you can do something that makes more sense.
Yeah.
Because I don't. I mean, we can, as Jan and Thomas deeper, we can talk about the design and the sensation and perception and all this stuff, and this is very good stuff. But then when you apply it to user needs, I mean, I'm really thinking, okay, does it make sense? And if we go to blind and low vision users, because as you know, my lab is focusing on that specifically, so we have been working on that many times. I mean, they don't mind following a very accurate path. This is not what they are asking actually, because there are different sets of skills that they have to get to navigate to the place, and different ways of providing them the information they need. So first is micro-navigation. Micro-navigation is, okay, can I go here and go between the table and the floor? And then you can provide some feedback for telling, okay, there is a path just in front of you on the right-hand side, and then you let them do. You don't want them to do exactly this path, but you want to provide them with the direction where to do. And then there is the second set of information they need is spatial awareness and orientation. So what is around me and what is the final destination? Are there different points, reaching points on the path that I should reach? So let's say I want to go there and there and there and there. So you just set the path in different... and this is something you can achieve, I guess, with the haptic feedback appropriately. But I'm really convinced that just following the path on the floor is not something they want. And if you design with them, they probably tell you, okay, I don't know. You provide me too much information. I can deal with my dog or cane. See what I mean?
Yeah, I agree that this device does not fit the needs of most visually impaired users, but maybe it would fit maybe some specific users' needs, but more on a guiding application of users that know how to, that can mostly perceive their environment and drive their wheelchair, but would need the help to get to a specific goal somewhere maybe in a building that they don't know, in an environment that they don't know, and in which case here the more guiding a longer path could be beneficial, but it fits really, a specific case and not the more global one.
Once again, I think that the chair can be better than the user, guiding along a path. Today, I mean, we can have chairs that deal very appropriately.
Yes, but I think that would depend on whether the user wants to just be transported by his wheelchair instead of navigating himself and choosing how he does so, given the information provided by a device.
Organizing a race with wheelchairs and
No, but
pilots, and this could be one achievement. Same kind of comments about the strategies. So what you call attractive and repulsive. So I guess that you have tried using your own device. So I read, so stimulis are played 200 millisecond burst every second.
Yeah.
So which is zzz, zzz,
yeah.
zzz. So imagine now you are working as a blind user and talking to your friend. So you are two of you and zzz, zzz. Do you think it's something useful?
Well, first, in cases where you are talking to someone on not actively navigating, one solution would be to disable the device, which could be detected using sensors, for instance. But here I think the task was given the small shape of the control environment and the tasks that we gave users, having one vibration every second was needed for participants not to get lost or move too far away from the path. But if it was to be used in real environments, probably this duration of between two haptic sensations could be modulated. If you are in a long corridor, you probably don't need to have one information every second. But if you are entering a zone where you have to make more turns and more specific navigation tasks, then in this case, the frequency at which the instructions are given could be augmented.
So I fully agree with you. You have to consider task and context. I mean, this is good. You did very good job. So we know the system is working. You can do that, and you've done a very nice path analysis. And even the method is good. It's something we can use to make sure that the guidance we provide is accurate. But then, as a researcher focusing on what is useful for blind users, I don't have a take-home message in this study because it's not usable. The way you provide information is not usable for them, and I'm sure they won't agree using it. Then, if you want to design something that may be used in this task and context, you have probably to organize workshops with them, asking what do they need exactly. Are they able to get 200 millisecond stimulus every second? Did they accept that? Because you can go to the innovation, put a product on the market, and then they won't buy it.
Yeah.
And then what for? I mean, so it's good, I would say, basic research, but then the application to blind and wheelchair for me is not.
Yeah, no, I would agree then that in order to really have this device used by real users, there is still a long way of design, discussion, and modification of everything that we did.
So I would really, maybe you know this book, but this is very interesting to me. I would recommend you to read the research methods in HCI, Human Computer Interaction, by Jonathan Lazard and colleagues, showing a set of design and participatory design methods you can use select interaction modality that is more appropriate and more acceptable to users. Because you have to consider many different factors when innovating designing new interaction. Is it useful? So can you achieve the task? Is it efficient? Can you achieve the task quickly? And what is the user experience with it? So is the user really agree to use this interaction in this device in real context? And sometimes you have very good achievement. So you do a pretty good job in efficiency, but you don't find.
Yeah.
Because it's not usable, and the user experience is very bad. So typically, having 200 millisecond vibration somewhere in the hand of the arm while working is probably a very bad user experience that they won't agree.
Okay. Yeah. That is something that should be considered in the.
So I just want to mention a few papers, and maybe you can you can read that we've done. So we are not experts in haptics in the lab. But as I mentioned, we are experts in designing technologies for blind users. So we have tried using attraction and repulsion along the path like 12 years ago. So there was a short paper showing that attraction is better than repulsion. So similar reason. But more recently, we have made a paper. So it's not guiding the whole body, but guiding the hand on the screen, let's say, on the drawing. And for me, the aim is the same. So guiding the body or guiding the hand, it's enough. So what have we done? On the back of the hand, we have 4 different actuators. And then we spend time with the users, blind users, asking, okay, how do you explore tactile drawing? So when you explore something that is tangible, what do you need? So they told us, okay, once I found the line, then I can follow the line, and then I go straight and quick until the next turn, and then I want to know if it's going to be left, right, or in front. So we designed just an interactions trying to provide indication about the length of the segment at the beginning, and then after this segment, will it be on the right or on the left? And if you read that paper, I think we got the award on this paper, you see that the path and the time, so efficiency, is much improved with the technique. Only 2 stimuli. So one is, you are this length from the next turn, and the next turn will be right.
I think that could be applied to navigation, but probably only in cases where there are long segments, I would say. So if there is a corridor, maybe you have the information of the length of the corridor, and then you have the turn information. Maybe in this case, in navigation, since you would take more time than just exploring with the hand, there might be a difference in the timing of the sensations, probably, given that we would walk a longer distance. Probably the information might have to be repeated or delayed once you get the turn.
Then when you want to apply to a different context, then you have to probably not redesign completely, but
adapt to the use case. Yeah.
Another paper that we submitted, we targeted, we compared Cartesian to coordinates, to Euclidean system. So how to provide, let's say, distance and direction around you. So one is x and y coordinates with the distance, and another one is polar coordinates. And you can provide on a grid.
Yeah.
And very quickly the users were able to say, okay, this is over there. And one of the coordinate system was much more efficient than the other. So this is, once again, different ways to provide awareness about the surroundings. So So this is probably something that you test in different contexts, because you can provide so many different stimulations with your devices.
Yeah, I think we could use it in really different ways. We explored some ways of doing that, but there's still a lot of them to explore.
So just one last question, because I'm running out of time. So I've read just during your defense, INRIA est le moteur de la recherche et de l'innovation numérique en France et en Europe depuis plus de 50 ans. So you are in an institute where the aim is to innovate.
Yeah.
And for me, what is really missing in your manuscript, and I'd like you to add something about that, is what is the market? I mean, because I'm not an expert, and I'm very interested in all you've done, but what is the market, and what is your contribution to eventually the market? Because you have run along all these very nice studies. Some of them I know, like PLO and etc. I've read the papers and I'm very interested in it. But now, okay, have you done something like everyone, or have you done something that does not exist and that can be turned into innovation or marketing product?
I would say that I'm not sure that our goal here is to, or as researchers, really to create a product that has to have a market and that would be sold or given that has to be really marketable and target a whole sufficient user base to be viable. Here, the uses might be, well, too specific and not that applicable yet to really large market.
Can you be more specific if we go to this handheld? I mean, I'm not an expert in devices, so I've seen many force feedback and vibrating joysticks. So is it something new that you have designed that could be integrated in the products in the next year, or is it something that already exists, actually?
Well, there are handles that provide localized feedback. Here, I would say that the innovation, the new thing about this device is that it is, we try to design it being easy to build, and so that maybe in the future we could allow users to create them themselves and to customize it later. So here, and I think this is also part of the Daniel project, the global objective is not to design one specific device that would be sold to a lot of users, but create a solution that could be adapted to the user-specific needs. This is not something that we covered here, but there are other PhD students in the team that are working on adapting the handle to the shape of one's hand. Then we would have also, we could explore the specification of the haptic feedback to these users, but then it would be more a unique product for one person than something that is really for a large market.
Okay, so I was not one of the reviewers of your manuscript, but I didn't spend hours on reading accurately. I'm not sure this is clearly mentioned as the context of your research, and I don't think it's clearly discussed at the end in your manuscript. Maybe I'm wrong.
The personalization might have been discussed in the perspective, but not in really in depth. So
it was missing to me because I don't know the market. I was wondering, reading it. Okay, I mean, can I do? Let's say with joystick I buy. Yeah.
I mean, you could, and that is part of the objective, is that this technology would be accessible to users. So if we give you the the specification of the handle, you can. The idea here is that if you have a 3D printer, you can make it quite easily yourself. Given that you have the skill to use a 3D printer, but
An engineer in Summit. Okay, thank you very much for inviting me. Thank you for the interest. Thank you for the supervisors inviting for this PhD, this PhD study. So we have one more questions.
Oh, good.
So it's time to give the floor to your supervisors, and we'll first offer Claudio to take the floor.
I don't have additional comments. More like a comments like a face to Pierre-Antoine. So great job, and it's now very high quality work, a lot of work, quality production, and I think we can safely say that the continued success of the Donald project is also thanks to all the work that we've done throughout all these years. And we have been able to run so many very interesting experiments and interactions with our critical teams in field, thanks to you and of course all the other people involved. And so I would like to not only praise the quality of the work and the quality of the work, but also how you were able to work very well in the team. Right? So helping all your colleagues and creating and fostering a very positive environment, because you know that collaborative projects sometimes are not easy, because especially multidisciplinary projects like this one. So I think you've been really great at creating a good environment, interacting with all the different teams, engineers, non-engineers, who sometimes not always easy to understand each other. You should be very proud of what you have done. And so maybe as a very small question, just what was the hardest thing that you had to do after?
did not think about this question. The other thing. Yeah, the defense might. No, yeah. Well, it's more on the personal side, but the writing was probably the most hard thing for me.
So thank you very much, Pierre-Antoine, for all these years. We had really wonderful time.
Thank you, Claudio. Marie, do you want to take the floor?
Yeah, I will just try to find the word in English. Okay, so first of all, congrats for all the work. Really different I can benefit to review and share this. I'm very happy, so happy to see that the expertise is staying. I appreciate your work so much. I'm very proud of that. Thanks so much, and Claudio. I really hope that this is not our last collaboration. Because as the discussions today have shown, we have new work has raised lots of open research questions, and I think that we have a lot of things to do with that. As we said, this work is part of the Donald project, and really it was a chance to work closely with and collaborate with the clinicians. I'm very happy that we can meet this year today to the defense, and I know that Marie is also on YouTube and watching you on YouTube. And that shows the spirit of the team, of the Donald team. And I think it is quite unique. And this is also, I can say, also to me. Just to give some context, as you said, the first step of the project was to conduct interviews, thanks to Karim and invitation from Pierre-Antoine, with end users and healthcare professionals. And this was your work, we learned on the conclusion that they you have raised, and on the successive also recommendation that and probably I will not insist enough on the numerous interactions that you have with them during your PhD. So of course, as you said, and Dr. Christophe here, the question, for example, of the morphology in another PhD work. But this is a complex task, especially when using these 3D printing, that's an open issue in this process. But of course, we'll see. But it was critical. And in terms of also of ethics, it was important to have one thing that can be evaluated by people. So we aim to design the universal, the customizable tool. And the challenge is to include not only blind people or religious people, but people with complex handicap. Yeah, we had lots of discussions about this. Yeah, I think lots of experience here. We also want to thank all the members of the team, as Claudia said, and that have participated or helped you during your PhD, because it's a collaborative work. And of course, you have collaborated with the others on behalf of the others, just have no particular order. So thanks to Louise, François, Thomas, Fred, Sylvain, Fabien, Sébastien, Eduardo, Maxime, I just want to say that I'm really impressed by the way you evolved during the 3 years. First, it's not really straightforward to have 3 supervisors, each having our own background and foolish ideas. And I have to say that you perfectly managed to tell us always in a subtle manner that we have to come back on Earth and follow your proposition. This is great because it means that you acquire an autonomy in your research work, and your scientific propositions were always relevant. So it's, I have to say, it was really nice also to see a computer science engineer and PhD student playing those mechatronics. I'm very proud of what you have done, particularly as you managed to go up to 3 years without users, which is a challenge. And so because you have to improve the reliability of your device, and master all, of course, the science, but the mechatronics, the software, the motion capture, and so that the trace you are now on a quantity accomplished researcher, and I just hope that you will have the opportunity to continue this work, because I think that you have many things to bring to the community. You make an excellent researcher, and to make it, one has to have human quality, and I have to say it was a pleasure to work with you. Thanks.
Thank you for this nice testimony. What do you want to take the last comments?
Yes, thank you, Mr. President. So I would like first to thank all the committee members for having accepted to be there today. So thanks to Jan and Thomas for reviewing the manuscript and for the review, and for being the president today. So thank you for all of this. You and we really appreciate that you are all here in person today. Then let's take it over to you, Pierre-Antoine. So I would like first to underline that I really greatly appreciated to work with you both on the scientific and relational sides. And the scientific part, so as Claudio and Manuel already underlined, so you were part of the project, and this project was quite multidisciplinary. These are like mechatronics, electronics, computer science, and also medical. On the medical side, we have like a lot of different like collaborations, and this was quite unique in terms of environment. I think you handled quite well this project. And besides this collaboration, on your side, you also propose new scientific contributions, and I would like to underline that you are able to manage both scientific but also technological contribution, and you have been able to build I would say software solutions, which is your background, but also hardware solutions, and you really improve your skills during these 3 years on that part, and usually when you have computer scientists are a little bit afraid of manipulating wires and just doing some manually stuff, and then you have been able to manage everything, and at the end you manage to have a collection of haptic devices, because this is not this is one of the hand prototypes that we have, but at the beginning we have a lot of different plastic stuff going on in your office. And so you managed to do this very well, and you managed, as it has been mentioned also, to conduct a lot of user studies. We all know that it is very time-consuming, and it requires a lot of effort to conduct all these experiments, and I really would like to underline this in your work. And as also it has been mentioned, you are always there to help your colleagues, with the students, engineers, and the team, so it was really appreciated. And I should also mention that even what you are doing in your research, you have been also able to translate this into teaching skills, and because you have been able to use what you are doing for teaching this to students in school, and I guess students also really appreciated to work on that project, and it was a great impact. So after this scientific aspect, of course, I will go a little bit on the relational side. So I really appreciate to work with you. You are a peaceful person, always be quite calm, and it's great to work with you. I guess you were a little bit stressed today.
Yeah, a bit.
Still, even if we can. It's only it's very, very difficult to perceive it, but I guess you are a little bit stressed still. But yes, I know you not since 3 years, but more years, because I got you as a student when you are an engineer, and since that time I saw you growing and really involving in your way of working on yourself, but working with others. And I have no doubt that you will do a good career, whatever you should in your next future, close or very far away futures. So I have no doubt that you will succeed in what you would like to do. And congratulations for all what you have done since today. And I wish you all the best of the future.
Thank you.
Thank you. So I think it's time now for us to yeah. So do we move or
Yeah,
we do?
Oui, on
Mettre comment, je sais
pas.
On peut peut-être même se mettre sur le côté. Hein. Comme ça, on voit à la fois la salle et le.
Soit monsieur le président.
Cher président. Vous devriez venir de notre côté, vous n'êtes pas évalué aujourd'hui. Il ne semble pas. Okay, so after deliberating, I give you the first shot of what we said, and we'll write it appropriately later. But in substance, the jury said that your work, Pierre-Antoine Cabaret, focuses on the design and evaluation of handheld haptic devices. The jury was impressed by the amount and the quality of the technical and scientific contributions, supported by excellent experimental studies. The jury was impressed by the different achievements related to prototyping, experimental design, statistical analysis, running evaluation, including people with special needs. We also highlight the interdisciplinarity between mechanical engineering and computer science, and methods, including methods coming from experimental psychology. We highlighted the educational, clear, and accessible nature of the oral presentation with high-quality visual illustration and slides, which made it possible to fully understand the amount of work that was carried out during the PhD. Your English was good, understandable, and the timing was good too. Finally, we consider that the answers to the questions were clear, relevant, and appropriate, demonstrating that your knowledge is good about the field. Your work has already given rise to many publications in very good venues. For all these reasons, we, the jury, congratulate you for the work that you have done, you have achieved during the PhD work, and we unanimously decide to award you with the grade of Doctor in Computer Science of Inside the Lab.
Thank you.
Before I give you the floor, we have two things to mention. First, we didn't ask for any modifications on your manuscript, formal ones, but we asked for informal ones. So according to the reports by the reviewers, and I will add a few suggestions, and you will have to manage that with your supervisors before providing the manuscript to the doctoral school. And the last thing I have to do, where is the... you have it. So you have to read the sermon in front of your peers.
Yeah, so
You can do it in French.
Oh yeah, I will switch to French because I have the version in French. Donc, en présence de mes pairs, parvenus à l'issue de mon doctorat en informatique et ayant ainsi pratiqué dans ma quête du savoir l'exercice d'une recherche scientifique exigeante, en cultivant la rigueur intellectuelle, la réflexivité éthique et dans le respect des principes de l'intégrité scientifique, je m'engage, pour ce qui dépendra de moi dans la suite de ma carrière professionnelle, quel qu'en soit le secteur ou le domaine d'activité, à maintenir une conduite intègre dans mon rapport au savoir, mes méthodes et mes résultats. Thank you. Je vais aussi faire mes remerciements en français, je pense que ça sera plus simple.
C'est le moment.
Je ne les ai pas écrits, donc je vais forcément oublier des gens. Déjà, merci à mes encadrants, Maud, Marie, Claudio, d'avoir été là tout le temps pour discuter et pour travailler ensemble. Merci aussi à tous les gens avec qui j'ai pu travailler durant la thèse. Je vais peut-être en oublier, on va essayer de faire une liste exhaustive. François, Fabien, Louise, Sébastien, je vais en oublier, c'est sûr. Guillaume, Thomas Howard aussi, Landy et Erwan, avec qui on a partagé des bureaux et beaucoup de choses. Merci aussi aux autres doctorants à l'INSA, Maxime, j'ai oublié des gens, Maxime, Eduardo, Théo, Maël, qui est arrivé récemment, mais voilà. Et voilà, merci à tout le monde. Je vais pas pousser plus loin que ça, je pense. Voilà, je pense. Oui, on va faire simple. On va faire simple. Et puis je vous invite au pot en salle 100 où il y a à manger et à boire.
The first one for you now.
Cabaret.
Congratulations.